In physics, a frame of reference consists of an abstract coordinate system and the set of physical reference points that uniquely fix the coordinate system in standardized measurements. In n dimensions, n+1 reference points are sufficient to fully define a reference frame. Using rectangular coordinates, a reference frame may be defined with a reference point at the origin and a reference point at 1 unit distance along each of the n coordinate axes. In Einsteinian relativity, reference frames are used to specify the relationship between a moving observer and the phenomenon or phenomena under observation. In this context, the phrase often becomes observational frame of reference, which implies that the observer is at rest in the frame, although not necessarily located at its origin. A relativistic reference frame includes the coordinate time, which does not correspond across different frames moving relatively to each other. The situation thus differs from Galilean relativity, where all possible coordinate times are essentially equivalent. Different aspects of frame of reference. The need to distinguish between the various meanings of frame of reference has led to a variety of terms. For example, sometimes the type of coordinate system is attached as a modifier, as in Cartesian frame of reference. Sometimes the state of motion is emphasized, as in rotating frame of reference. Sometimes the way it transforms to frames considered as related is emphasized, as in Galilean frame of reference. Sometimes frames are distinguished by the scale of their observations, as in macroscopic and microscopic frames of reference. In this article, the term observational frame of reference is used when emphasis is upon the state of motion rather than upon the coordinate choice or the character of the observations or observational apparatus. In this sense, an observational frame of reference allows study of the effect of motion upon an entire family of coordinate systems that could be attached to this frame. On the other hand, a coordinate system may be employed for many purposes where the state of motion is not the primary concern. For example, a coordinate system may be adopted to take advantage of the symmetry of a system. In a still broader perspective, the formulation of many problems in physics employs generalized coordinates, normal modes or eigenvectors, which are only indirectly related to space and time. It seems useful to divorce the various aspects of a reference frame for the discussion below. We therefore take observational frames of reference, coordinate systems, and observational equipment as independent concepts, separated as below. An observational frame is a physical concept related to state of motion. A coordinate system is a mathematical concept, amounting to a choice of language used to describe observations. Consequently, an observer in an observational frame of reference can choose to employ any coordinate system to describe observations made from that frame of reference. A change in the choice of this coordinate system does not change an observer's state of motion, and so does not entail a change in the observer's observational frame of reference. This viewpoint can be found elsewhere as well, which is not to dispute that some coordinate systems may be a better choice for some observations than are others. Choice of what to measure and with what observational apparatus is a matter separate from the observer's state of motion and choice of coordinate system. Here is a quotation applicable to moving observational frames and various associated Euclidean three-space coordinate systems, r, etc., and this on the utility of separating the notions of an r, etc., and this, also on the distinction between im, r, etc., and from J. D. Norton. The discussion is taken beyond simple space-time coordinate systems by Brading and Castellani. Extension to coordinate systems using generalized coordinates underlies the Hamiltonian and Lagrangian formulations of quantum field theory, classical relativistic mechanics, and quantum gravity. Coordinate systems. Although the term coordinate system is often used in a non-technical sense, The term coordinate system does have a precise meaning in mathematics, and sometimes that is what the physicist means as well. A coordinate system in mathematics is a facet of geometry or of algebra, in particular, a property of manifolds. The coordinates of a point are in an n-dimensional space is simply an ordered set of n numbers. In a general Banach space, these numbers could be coefficients in a functional expansion like a Fourier series. In a physical problem, they could be space-time coordinates or normal mode amplitudes. In a robot design, they could be angles of relative rotations, linear displacements, or deformations of joints. Here we will suppose these coordinates can be related to a Cartesian coordinate system by a set of functions, where x, y, z, etc. are the n-Cartesian coordinates of the point. Given these functions, coordinate surfaces are defined by the relations. The intersection of these surfaces define coordinate lines. At any selected point, tangents to the intersecting coordinate lines at that point define a set of basis vectors e1, e2, n at that point, that is, which can be normalized to be of unit length. For more detail see curvilinear coordinates. Coordinate surfaces, coordinate lines, and basis vectors are components of a coordinate system. If the basis vectors are orthogonal at every point, the coordinate system is an orthogonal coordinate system. An important aspect of a coordinate system is its metric tensor GIK, which determines the arc length ds in the coordinate system in terms of its coordinates, where repeated indices are summed over. As is apparent from these remarks, a coordinate system is a mathematical construct, part of an axiomatic system. There is no necessary connection between coordinate systems and physical motion. However, coordinate systems can include time as a coordinate, and can be used to describe motion. Thus, Lorentz transformations and Galilean transformations may be viewed as coordinate transformations. General and specific topics of coordinate systems can be pursued following the see also links below. Observational frames of reference. An observational frame of reference, often referred to as a physical frame of reference, a frame of reference, or simply a frame, is a physical concept related to an observer and the observer's state of motion. Here we adopt the view expressed by Kumar and Balve. An observational frame of reference is characterized only by its state of motion. However, there is lack of unanimity on this point. In special relativity, the distinction is sometimes made between an observer and a frame. According to this view, a frame is an observer plus a coordinate lattice constructed to be an orthonormal right-handed set of space-like vectors perpendicular to a time-like vector. See therein. This restricted view is not used here, and is not universally adopted even in discussions of relativity. In general relativity, the use of general coordinate systems is common. There are two types of observational reference frame: inertial and non-inertial. An inertial frame of reference is defined as one in which all laws of physics take on their simplest form. In special relativity, these frames are related by Lorentz transformations, which are parametrized by rapidity. In Newtonian mechanics, a more restricted definition requires only that Newton's first law holds true, that is, a Newtonian inertial frame is one in which a free particle travels in a straight line at constant speed, or is at rest. These frames are related by Galilean transformations. These relativistic and Newtonian transformations are expressed in spaces of general dimension in terms of representations of the Poincare group and of the Galilean group. In contrast to the inertial frame, a non-inertial frame of reference is one in which fictitious forces must be invoked to explain observations. An example is an observational frame of reference centered at a point on the Earth's surface. This frame of reference orbits around the center of the Earth, which introduces the fictitious forces known as the Coriolis force, centrifugal force, and gravitational force. Measurement apparatus. A further aspect of a frame of reference is the role of the measurement apparatus attached to the frame. This question is not addressed in this article, and is of particular interest in quantum mechanics, where the relation between observer and measurement is still under discussion. In physics experiments, the frame of reference in which the laboratory measurement devices are at rest is usually referred to as the laboratory frame or simply lab frame. An example would be the frame in which the detectors for a particle accelerator are at rest. The lab frame in some experiments is an inertial frame, but it is not required to be. In particle physics experiments, it is often useful to transform energies and momenta of particles from the lab frame where they are measured, to the center of momentum frame, COM frame, in which calculations are sometimes simplified, since potentially all kinetic energy still present in the COM frame may be used for making new particles. In this connection it may be noted that the clocks and rods often used to describe observers' measurement equipment in thought, in practice, are replaced by a much more complicated and indirect metrology that is connected to the nature of the vacuum, and uses atomic clocks that operate according to the Standard Model and that must be corrected for gravitational time dilation. In fact, Einstein felt that clocks and rods were merely expedient measuring devices and they should be replaced by more fundamental entities based upon, for example, atoms and molecules. Types: body fixed frames of reference, space fixed frames of reference, inertial frames of reference, non-inertial frames of reference. Examples of inertial frames of reference. Simple example: consider a situation common in everyday life. Two cars travel along a road, both moving at constant velocities. See Figure 1. At some particular moment, they are separated by 200 meters. The car in front is traveling at 22 meters per second and the car behind is traveling at 30 meters per second. If we want to find out how long it will take the second car to catch up with the first, there are three obvious frames of reference that we could choose. First, we could observe the two cars from the side of the road. We define our frame of reference, S, as follows. We stand on the side of the road and start a stop clock at the exact moment that the second car passes us, which happens to be when they are a distance d equals 200 meters apart. Since neither of the cars is accelerating, we can determine their positions by the following formulas. Where is the position in meters of car 1 after time t in seconds and is the position of car 2 after time t? Notice that these formulas predict at t equals 0 s the first car is 200 meters down the road and the second car is right beside us, as expected. We want to find the time at which, therefore we set and solve for, that is. Alternatively, we could choose a frame of reference S, situated in the first car. In this case, the first car is stationary and the second car is approaching from behind at a speed of v2 minus v1 equals 8 meters per second. In order to catch up to the first car, it will take a time of d, v2 minus v1 equals 208 s, that is, 25 seconds, as before. Note how much easier the problem becomes by choosing a suitable frame of reference. The third possible frame of reference would be attached to the second car. That example resembles the case just discussed, except the second car is stationary and the first car moves backward towards it at 8 meters per second. It would have been possible to choose a rotating, accelerating frame of reference, moving in a complicated manner, but this would have served to complicate the problem unnecessarily. It is also necessary to note that one is able to convert measurements made in one coordinate system to another. For example, suppose that your watch is running 5 minutes fast compared to the local standard time. If you know that this is the case, when somebody asks you what time it is, you are able to deduct 5 minutes from the time displayed on your watch in order to obtain the correct time. The measurements that an observer makes about a system depend therefore on the observer's frame of reference. Additional example: for a simple example involving only the orientation of two observers, consider two people standing, facing each other on either side of a north-south street. See Figure 2. A car drives past them heading south. For the person facing east, the car was moving toward the right. However, for the person facing west, the car was moving toward the left. This discrepancy is because the two people use two different frames of reference from which to investigate this system. For a more complex example involving observers in relative motion, consider Alfred, who is standing on the side of a road watching a car drive past him from left to right. In his frame of reference, Alfred defines the spot where he is standing as the origin, the road as the x-axis, and the direction in front of him as the positive y-axis. To him, the car moves along the x-axis with some velocity v in the positive x direction. Alfred's frame of reference is considered an inertial frame of reference because he is not accelerating. Now consider Betsy, the person driving the car. Betsy, in choosing her frame of reference, defines her location as the origin, the direction to her right as the positive x-axis, and the direction in front of her as the positive y-axis. In this frame of reference, it is Betsy who is stationary and the world around her that is moving. For instance, as she drives past Alfred, she observes him moving with velocity v in the negative y direction. If she is driving north, then north is the positive y direction. If she turns east, east becomes the positive y direction. Finally, as an example of non-inertial observers, assume Candice is accelerating her car. As she passes by him, Alfred measures her acceleration and finds it to be a in the negative x direction. Assuming Candice's acceleration is constant, what acceleration does Betsy measure? If Betsy's velocity v is constant, she is in an inertial frame of reference, and she will find the acceleration to be the same as Alfred in her frame of reference, or in the negative y direction. However, if she is accelerating at rate a in the negative y direction, she will find Candice's acceleration to be a equals a minus a in the negative y direction, a smaller value than Alfred has measured. Similarly, if she is accelerating at rate a in the positive y direction, she will observe Candice's acceleration as a equals a plus a in the negative y direction, a larger value than Alfred's measurement. Frames of reference are especially important in special relativity, because when a frame of reference is moving at some significant fraction of the speed of light, then the flow of time in that frame does not necessarily apply in another frame. The speed of light is considered to be the only true constant between moving frames of reference. Remarks: it is important to note some assumptions made above about the various inertial frames of reference. Newton, for instance, employed universal time, as explained by the following example. Suppose that you own two clocks, which both tick at exactly the same rate. You synchronize them so that they both display exactly the same time. The two clocks are now separated and one clock is on a fast-moving train, traveling at constant velocity towards the other. According to Newton, these two clocks will still tick at the same rate and will both show the same time. Newton says that the rate of time as measured in one frame of reference should be the same as the rate of time in another. That is, there exists a universal time and all other times in all other frames of reference will run at the same rate as this universal time irrespective of their position and velocity. This concept of time and simultaneity was later generalized by Einstein in his special theory of relativity, where he developed transformations between inertial frames of reference based upon the universal nature of physical laws and their economy of expression. It is also important to note that the definition of inertial reference frame can be extended beyond three-dimensional Euclidean space. Newton's assumed a Euclidean space, but general relativity uses a more general geometry. As an example of why this is important, let us consider the geometry of an ellipsoid. In this geometry, a free particle is defined as one at rest or traveling at constant speed on a geodesic path. Two free particles may begin at the same point on the surface, traveling with the same constant speed in different directions. After a length of time, the two particles collide at the opposite side of the ellipsoid. Both free particles traveled with a constant speed, satisfying the definition that no forces were acting, no acceleration occurred, and so Newton's first law held true. This means that the particles were in inertial frames of reference. Since no forces were acting, it was the geometry of the situation which caused the two particles to meet each other again. In a similar way, it is now common to describe that we exist in a four-dimensional geometry known as space-time. In this picture, the curvature of this 4D space is responsible for the way in which two bodies with mass are drawn together even if no forces are acting. This curvature of space-time replaces the force known as gravity in Newtonian mechanics and special relativity.